Hey there, I'm Nagar, and in this video I decided to discuss about what is Big O. And I'm going to visualize different Big O runtimes for famous algorithms. To begin with, we can imagine, to give you a better understanding of what is really Big O and what's the big fuss about Big O, imagine that you have to draw 16 boxes on a piece of paper. In order to do that, you can take two ways to get this job done. The first way, let's call it algorithm number one, you can draw 16 boxes at a time, which would take 16 steps. So the output or the operation or the big O runtime of your first algorithm would be 16. Let's go with the second solution or second way, or let's call it algorithm number two. In this algorithm, instead of draw each and every box at a time, you can use folding paper. You can fold it once with one fold, twice, you are going to have four boxes, three times folding will give you eight boxes, and by four folds, you are going to have 16 boxes. So you can draw twice as many boxes with every fold, which is quite faster than the first solution. So what is the running time for this algorithm? The answer is the steps was four steps, and if you are going to actually compare it with the first solution, the algorithm number one would take on times, which is 16 steps, but this algorithm number two, would take O log n times, which would be for 16 boxes, log 16 would give us 4. So in 4 steps, we've done the job, which is quite faster in comparison with the first solution. So here we represent some common big O runtimes with the help of different algorithms. The first one is, actually I sorted them from the fastest to the slowest one. The first one is O log n, or log time. We know it as log time, which is quite fast. And we can, example, binary search is such algorithm that the runtime of this algorithm is O log n. The second one is ON, also known as linear time, for example, simple search. ON multiplied log n, which is famous for fast sorting algorithms. For example, quicksort would take such a time. The next one is O and 2, which is known as a slow sorting algorithm. For example, selection sort. Runtime is O and 2. And the last one is ON factorial, which is really, really slow algorithm. For example, traveling salesperson research algorithm, which we discuss in upcoming videos in this series of, discussing about algorithms. If you use the first algorithm, it will take you O log n. For example, if you use binary search, you can do it by 10 operation per second, which will take 4 operation to draw 16 boxes or 16 grid. So it will take you 0.4 seconds to draw the grid. If you actually have to draw 1024 boxes, it will take log 1024, which is 10 operations, or 1 second to draw a grid of 1024 boxes, which is quite fast. Here, actually, we can see that the runtime to complete a task or operation in steps or in operations, and it depends to the size of input of data for each and different algorithm that we earlier discussed about them. You can see graph of them, and let's compare them in boxes. For example, if we have two draw 16 boxes with O log n, for example, binary search, it would take 0.4 seconds to draw 16 boxes. And as it grows, it is fast in compare with the other algorithms, which is gets quite slower when the size of input data increases. So if we use, for example, ON with 16 boxes, we have to spend 1.6 seconds, 256, 25.6 seconds, and with 1024 boxes to draw them. It would take us 1.7 minutes. With other algorithm, as you can see, when we reach to O(n) factorial algorithm, and if you want to draw 256 boxes, actually, it would take years to get this job done. And it gets worse when it comes to 1024 boxes. It gets freaking years, and it gets, it drives us crazy if we want to, take actually get this job done and draw 1024 boxes with O(n) factorial runtimes. It would take years, and you can easily compare and, you know, see that which algorithm is more beneficial and it has better efficiency when we put it in this way and when we compare all of them together. The main takeaways are as follows. Algorithm speed is measured in growth of the number of operations. We do not measure them in seconds or anything else. The only thing that matters is the number of operations. The second important point that we have to stick in our mind is how quickly the runtime of an algorithm increases as the size of the input, as we saw earlier when we wanted to draw 16 boxes with the help of O(n) factorial would take days to get this job done, and it is crazy. Last but not least point is O log n is faster than ON, and it gets faster as the list of items we search in grows actually by the time. Okay, that's it. It's all you have to know about big O, which is a quite important concept when we want to measure the output, measure in any ways an algorithm and its efficiency. So see you in the next video. So stay tuned.